Hello young minds, welcome to another session of All Force e-learning program. Now this is session number 64. Now in this session we will discuss about the applications of the potential difference with electric field. The relation between potential difference and electric field. We will take up the applications of this. Now in the first one, let us derive the formula for the electric potential due to a linear charge. You are asked to find the electric potential for a linear charge distribution. So there is a line of charge like this. A line of charge, linear charge, positively charged like this. A line of charge, positively charged. Now with respect to this line of charge of linear charge density lambda, now he is asking you to find out what is the electric potential due to this at a point P, somewhere here at a point P, which is at a distance R. He is asking you to find the electric potential due to this, right? Now we know according to, we have already studied, I have already stated, electric potential is the state of a body which determines the direction of flow. And potential is the amount of work done in moving the charge from infinite distance to the point in the charge. Potential difference is the work done to move the charge from one point to another point, right? And I have even stated the relation electric field strength is minus dV by dr, or dV I can write as minus E dr. So the electric potential is the work done. And electric field strength actually E is equal to, E is the force experienced by unit positive charge. Now in the process of deriving the formula between these two, so look here, potential difference delta V is equal to work done per unit charge. But work done, the small work done in moving a charge is integral of F dot dr. Work done is F dot dr. So the work done I can write as, it is integral of force, it's EQ. F I can write as F is equal to EQ naught dot dr. So the work done is Q naught times E dot dr it is. Work done. So Q naught this side. So work done dW by Q naught is integral E dot dr. But dW by Q naught is work done. So potential difference dV, W by Q naught against the field. So it's minus of E dot dr it is. So therefore, potential difference is minus integral E dot dr. And E I can write as, from this I can write as E is minus dV by dr. So the relation electric field strength is the negative of the potential gradient. Electric field intensity is the negative of the potential gradient in that field between any 2 points there. Or dV is equal to minus E dr. If I integrate on both sides, the potential difference V final minus V initial is minus integral initial to final E dot dr. So this is the final statement of the potential difference. So this is the relation what we have got. Using that relation, we are going to derive the formula for the electric potential due to a linear charge, line of charge there. So we know that linear charge density, I have explained you while explaining charges. Linear charge density lambda is equal to charge per unit length Q by L. Well, if I take a particular length, then charge is lambda into L. So at a point P, if you have to find out the electric potential, electric potential according to the definition, it is the work done in moving the charge from infinity to the point in the field. Work done to move the charge from infinity to the point in the field. Well, we have to find out the relation based on the, we have to find out the formula for potential based on the potential relation between potential and electric field. We have derived in Gauss law, the electric field due to a linear charge. The electric field due to a line of charge, the electric field intensity of a line of charge, linear charge, E is given as 1 by 4 pi epsilon naught 2 lambda by R. It's 1 by 4 pi epsilon naught 2 lambda by R for an infinite long linear charge of uniform charge distribution lambda. This is an infinite long linear charge distribution there. So electric field due to a linear charge of infinite length, it's 1 by 4 not 2 lambda by r. and according to the relation between the potential and electric field, we can write this as so electric field due to the linear charge, it's 1 by 4 pi epsilon naught 2 lambda by r. Now coming to the derivation of the thing there, we know according to the definition of electric potential, dV is equal to work done per unit charge against the field. The potential difference is work done per unit charge against the field, or dV is equal to work done, so it's F dot dr by Q dot, but F by Q naught is nothing but against the field minus, or dV I can write as F by Q naught is E dot dr. Well, the potential at this point, a small potential between 2 point dV I can write as minus E dr. So integrating on both sides, potential difference between dV, integral dV is minus integral E dot dr between the initial and final point. If this is the yes, so potential dV integral is minus, integrating on both sides, integral dV is minus integral of initial point to final point E dot dr. Right, so integrating, it's V final minus V initial is minus integral initial to final E dot dr. Well, suppose if I take the initial point to be at infinity, so initial point at infinity, final point at P, so it's potential at P minus potential at infinity, it's minus infinity to point P, so at a distance R, it's E dot dr. So substituting, well, we know potential at infinity is 0, so potential at the point P is equal to minus integral of E, so E is, we know for the linear charge it is 1 by 4 pi epsilon naught 2 lambda by r dr it is. So potential at any point, it's 2 lambda by 4 pi epsilon naught integral 1 by r dr. Well, we know integration of 1 by r is log, integral 1 by x dx, integral of 1 by x dx is equal to log x. So substituting potential at the point minus 2 lambda by 4 pi epsilon naught log r plus c, some constant. So therefore the potential due to a linear charge I can write as 2 lambda by 4 pi epsilon naught log r plus the constant of proportionality. Suppose if I have to find out the potential difference between 2 points A and B, suppose there are 2 points at a distance A and B, then so we know potential difference between 2 points delta V AB, potential difference, it's VB minus VA. So potential at B minus potential at A can be written as, it is minus 2 lambda. From here we derive 2 lambda by 4 pi epsilon naught, it's integral 1 by r dr from A to B. So potential at B minus potential at A is minus 2 lambda by 4 pi epsilon naught, 1 by r is log r between the limits A and B. So VB minus VA I can write as 2 lambda by 4 pi epsilon naught log r, taking minus, I can reverse the limits, so it's BA. So VB minus VA is equal to 2 lambda by 4 pi epsilon naught log A minus log B. So finally the potential difference between 2 points VB minus VA is 2 lambda by 4 pi epsilon naught log of A by B. So this is the formula for the potential difference between 2 points for a linear charge distribution like this. So this way we can find the potential for the linear charge. In another example, another illustration, we are now asked to derive the potential due to a infinite charged sheet. Suppose there is an infinite charge sheet like this, uniformly charged, insulating, non-conducting infinite charge sheet of surface charge density sigma. Well, we know for a non-conducting surface charge density, for non-conducting infinite sheet, charged sheet, we know the electric field strength E is sigma by 2 epsilon naught, and we know dV is equal to minus E dr. Well, using these two, we can derive the formula for the electric potential due to the infinite charge sheet at a point P. Consider a point P at a distance R. So here, so dV is equal to minus E dot dr. So potential difference E. So integrating on both sides. So potential potential V between the limits from infinity to point P, or if I take potential at infinity 0, so the potential V I can write as minus integral E dr, because the radius vector and the electric field vector both are in same direction. So V is minus integral of E sigma by 2 epsilon naught dr. So V is sigma by 2 epsilon naught integral dr. So we can be written as minus sigma by 2 epsilon naught into R plus C. In general, it is sigma by 2 epsilon naught into R plus C. Had it been a conducting sheet, then the electric field would have been sigma by epsilon instead of sigma by 2 epsilon. So sigma by epsilon here, instead of here sigma by 2 epsilon, I should substitute as sigma by epsilon. So I will be getting, for a conducting sheet, it is minus sigma by epsilon into R plus C. If I consider 2 points A and B, so the potential difference VB minus VA is minus integral E dot dr A to B. So VB minus VA is minus integral A to B sigma by 2 epsilon naught dr. Well, both are in same direction, dot product cos 0 1, so E dr. So VB minus VA is equal to minus sigma by 2 epsilon naught integral dr A to B, or VB minus VA is equal to minus sigma by 2 epsilon naught, it is R between the limits A and B, or VB minus VA is taking minus inside, reversing the limits, sigma by 2 epsilon naught into R, it's BA. So finally, potential difference between 2 points VB minus VA is equal to sigma by 2 epsilon naught upper limit minus lower limit, it's A minus B. So this way you can find out the potential difference between 2 points due to a infinite charged sheet. Potential difference between B and A, so VB minus VA, it's sigma by epsilon naught A minus B, like this. Okay, so this way for infinite sheet. A question was given based on this one. A sphere of radius R, a charged sphere of radius R, has a potential difference V between the points on the surface and at a point which is at a distance 3r. There is a charged sphere like this. For a charged sphere of radius R, the potential difference between surface point and point P is V. Well, point P is at a distance 3r. He is asking to find out what is the electric field on the surface. The question is, for a charged sphere of radius R, the potential difference between the surface and point P is V. Then find the electric field on the surface. This is the question. Now in this question, he has not given a charge of the sphere. He didn't give you the charge. Let the charge on the sphere be some q. Then we know. So if the charge of the sphere, charge of the conducting sphere is q and the radius is r, then we can find the potential at the point P as 1 by 4 pi epsilon naught. We know the potential at an outside point is q by r. So potential at point P 1 by 4 pi epsilon naught charge q by r, the distance of the point is 3r. First point. Similarly, potential on the surface, we know on the surface the potential is 1 by 4 pi epsilon q by its radius r. So therefore potential difference between surface and point P is Vs minus Vp. So it's 1 by 4 pi epsilon naught q by r minus 1 by 4 pi epsilon naught q by 3r. This potential difference is given as V. So therefore, from this we can simplify. V is, let me take the common things out. 4 pi epsilon naught q by r is common out. So it's 1 minus 1 by 3. So V is equal to 1 by 4 pi epsilon naught. It's 2q by 3r. This is equation 1. So potential difference. In the question he has given the potential difference between the surface and point P is V. If the potential difference between the surface and point P is V, then what is the electric field at the surface point of the sphere? This is a conducting charged sphere of radius r. So conducting charged sphere of radius r, then the question, if the potential difference between surface and the point P is V, then what is the electric field on the surface? So first, let the charge, he has not given the charge. Let us consider the charge on the sphere be q. Then the potential, we know potential at any point, outside point is 1 by 4 epsilon q by r. So at a point P which is at a distance 3r, potential is 1 by 4 epsilon q by 3r. Then potential on the surface 1 by 4 epsilon q by r. So potential difference, substituting, the first relation we get is V is 1 by 4 epsilon 2q by 3r. Now, we know the formula for the electric field on the surface. Electric field on the surface is 1 by 4 pi epsilon naught q by, the radius is r square. Equation 2. Now dividing 2 by 1. So V potential difference, it is given as V. We have found, deduced it as 2q by 3r. Right? So it's 3 minus 1 by r it is. So therefore 2q by 3r. Dividing both, we get it as, so r like this. So therefore the potential difference between the surface point and the outside point is q by 3r and the surface point is 1 by 4 pi epsilon q by r. Then the potential difference between these two, outside point P, surface point. So Vs minus Vp is given as V. 1 by 4 pi epsilon q by r minus 1 by 4 epsilon q by 3r. Taking common things out, 1 by 4 pi epsilon q by r common. 1 minus 1 by 3, it is 2q, it's 2 by 3, 3 minus 1, 2 by 3. So 2q by 3r is the potential difference V. Right? So the electric field on the potential, so V, electric field. So dividing both, this cancel, q, r also cancel, 3 goes out. So electric field on the surface by potential V is equal to 1 by r, 1 by 1, this r by 2 by 3, 3 goes up, it's 3 by 2r. So cross multiplying, electric field on the surface is 3v by 2r. This is the formula. If the same question is asked like this, suppose if he says same question, instead of asking you to find the electric field on the surface, if he is asking you to find the electric field at the point P, then what would be the thing there? The question, same question is now repeated in this manner. If the potential difference between the surface and point P, surface and point P is V, then electric field at point P is dash. Same question, same. So again we know the formula for the potential at any point is 1 by 4 pi epsilon naught q by r. Let the charge be q. So at the point P potential, it's q by 3r. Well, potential on the surface Vs, it's 1 by 4 pi epsilon naught charge q by r. So given the potential difference between surface and point P is V. So potential difference between surface and point P, V is Vs minus Vp, or V is 1 by 4 pi epsilon naught q by r minus 1 by 4 pi epsilon naught q by 3r it is. So V is 1 by 4 pi epsilon naught q by r common, it's 1 minus 1 by 3. I will get it as 1 by 4 pi epsilon naught, 1 minus 1 by 3 is 2 by 3, it's 2q by 3r, equation 1. But this time he has asked to find the electric field at point P. We know electric field at any outside point is 1 by 4 pi epsilon q by r square. So therefore, electric field at any outside point E, it's 1 by 4 pi epsilon naught charge q by, now the distance of the point is 3r. 3r whole square it is. So this is equation 2. So dividing 2 by 1, V is 1 by 4 pi epsilon naught q. 2q by 3r we have got. So dividing both, so 1 by 4 pi epsilon, 1 by 4 epsilon naught q cancel. So E by V is, this will go to the numerator, this down. It's 3r by 2 times 3r into 3r. So 1 3r gets cancelled. E by V is 1 by 6r. So cross multiply. Electric field is V by 6r at the outside point. In the earlier question, we have found the electric field on the surface point. Now it is the electric field at the outside point. Point P, so the electric field is V by 6r. So potential difference between 2 points he has given, right? 2 points with distance, of course. Then he is asking to find the electric field at either of the point, either this point or that point, right? So then this is for a charged conducting sphere where the charge is distributed only on the surface, no charge inside, no field inside, no flux inside, potential inside remains constant. Well, if in this one the potential difference between center and surface will be 0. He can even ask the question like this also. Instead of surface, he will give you the potential difference between the center and the point P is V. Well, the potential at the center and the potential at the surface is same. So, if the potential difference between center and point P is V, then same method. Because at the center the potential is same as on the surface. Because this being a conducting sphere, conducting charged sphere, this is a conducting charged sphere. So, the potential at any point inside is a constant. Whether it is center or surface or inside. Even inside point also. Potential difference between any inside point and outside point is V. Inside and outside point is V. Then what is the electric field? He can ask you to find out the electric field at any point. Well, at any inside point the field is 0. Electric field at the center or electric field inside is 0. On the surface you can find, or any outside point also you can find. So this way he will give you the potential difference between 2 points and he will ask you to find the electric field at any respective point. So that way you can find out the relation for the electric field potential, right? So question, you please see, the question can be between surface and the outside point, it can be between inside point and outside point, or it can be between center and outside point. The formula remains the same, the method remains the same. The method is same and the electric field derivation is also same there. So this way you can find out. Now, the electric potential, there are two concentric spheres of charge Q1 and Q2. Two concentric charged spheres of charge Q1, Q2, radius A and B. Right? Now the question is, what is the potential difference between the inner surface of the inner sphere and the outer surface of the outer sphere? Potential difference between the potential at this point, let the point here be, let us say some x and this is y. So potential difference between x and y, potential difference between x, y. So potential at x, potential at y. So potential difference between the point x and point y. So it's Vx minus Vy. You know, Vy is the surface point for the outer sphere and it is outside point for the inner sphere. So at this point if you find the potential, it's 1 by 4 pi epsilon. For the inner sphere, it is the outside point which is at a distance, the radius is B. So therefore for the inner sphere of charge Q1, it is the outside point of distance B. Plus the potential, it is the point on the surface of the second sphere. It's 1 by 4 pi epsilon naught Q2 by on the surface it is P. So potential at y is 1 by 4 pi epsilon naught. B is LCM Q1 plus Q2. Or Q1 by B plus Q2 by B. Okay. Similarly, taking the potential at x, Vx. Now this is the surface point of the inner sphere, 1 by 4 pi epsilon naught, it's Q1, first sphere Q1, the distance of the point is A, plus for the point x is the inside point of the outer sphere, The potential at the inside point is same as on the surface point. So it's 1 by 4 pi epsilon naught q2 by b. Well, the potential difference, substituting, it's 1 by 4 pi epsilon naught q1 by a plus 1 by 4 pi epsilon naught q2 by b minus the potential at y. 1 by 4 pi epsilon naught q1 by b plus 1 by 4 pi epsilon naught q2 by b. Now here it is plus q2 by b minus of, if I multiply this term will get cancelled. So the potential difference is, potential difference between x and y, xy, it's 1 by 4 pi epsilon naught q1 by a minus q1 by b. So potential difference is independent of the charge on the outer sphere. So delta V is equal to 1 by 4 pi epsilon naught q1 bracket 1 by a minus 1 by b. It's independent of the charge on the outer sphere. Suppose some extra charge is given to the outer sphere. This is a previous entrance question. First, the potential difference between these 2 points is V. Now, when extra charge is given to the outer sphere 3q, then what is the potential difference? The potential difference between these 2 points is independent of the outer charge. The charge on the outer sphere. It's q1 by 1 by a minus 1 by b. So, this way you can find out the potential. The potential, two conducting charge spheres. These are the two conducting hollow charge spheres, hollow spheres. Well, then the potential difference between the surface of the inner sphere and outer sphere. Now, this potential difference is independent of the charge on the outer sphere. You know, you can take the point at any point, inside point or center point. Any point, the first point may be anywhere inside, and the outer second point is on the surface. So potential difference between any point inside and the potential on the surface. Now this difference is independent of the charge on the outer sphere. Take any point inside, the potential difference depends only on the first charge and the distance of the respective distance of those points. But it is independent of the charge on the outer sphere. Any extra charge added to it, any extra charge removed from it, whatever it is, any change that is taking place for this outer sphere does not affect the potential difference between the inside point and the surface point, outer surface point of this system there. Okay, right, thank you.